Okay, how to determine the concavity interval inflection point for f of x is equal x to power 8 natural logarithm x. So to identify concavity for any function f, first we need to get the second derivative and identify the positivity for the interval. If the the interval where second derivative is positive, let me write down around point x0, let's say. If it's positive, greater than 0, then we have concavity up. Concavity up. But if the second derivative around point x0, so that's just a point on some certain interval, is less than 0, then we get concavity down. Okay? And if we have second derivative on interval where x0 is located is equal 0, hence we're gonna have the inflection point for the function if around this function f, let's say, let me go like this, around function f, the if we take a small neighborhood for the function, let's say this piece, right? Here is, so the value on the left side of point x and right side of the point x, they are located on the opposite sides of this point, right? See, this area located on the right side and this is located on the left side. If it's the surroundings, the nearby surroundings of that point are located on opposite sides of the point x0, that means we are having inflection point, and that's in the case when second derivative is 0. So in this specific case, f of x is equal x to power 8 natural logarithm x. So we have our restriction is going to be the domain that has to be all positive, right? Because natural logarithm can be positive real numbers. Okay, so let's take first derivative. Before we move to second, first we have to take first derivative, right? First derivative of x, since we have here product, so I'm going to apply for derivative u v prime equal u prime v plus v prime u. Yes? Okay. So derivative of x to power 8 is going to be 8x to power 7 and times natural logarithm x, right? And then plus, excuse me, derivative of v, which is logarithm x, it's going to be 1 over x. Derivative of natural logarithm x is 1 over x. And x to power 8, we multiply. Okay? So from here, what do I have? I can take this x to power 7 as a common factor, take out, and I will have 8 natural log x plus 1 here. Okay, now let's take second derivative. Second derivative, oops. Second derivative is equal So we take again derivative of 7, x to power 7. So again, we have product rule for the derivative. So it's going to be 7x to power 6 times 8 natural log x plus 1. We have second derivative down, right, less than 0. And on the right side, we have second derivative up. Let me write down here. That's why. Okay, and that's it. We already know the intervals. On interval where x point is greater than e to power negative 15 over 56, the function is concave up. When x is between 0 and e to power negative 15 over 16, the function is concave down. And when x is equal e to power negative 15 over 56, we figured out that we have inflection point. Okie dokie. Plus, now we take derivative of v, which is in our case 8 logarithm x plus 1. So it's going to be logarithm x is going to be 1 over x, right? 8 stays there. So instead of 1, I put here 8. And the derivative of 1, it's going to be 0. And I multiply by x to power 7. Yes? Okay. So let's see what we can do here in this case. Let me rewrite 7 nicer. So from here, what I can do, I'm taking x to power 6. And what we have in parentheses left, we get 7 times 8 natural log x plus 1. Let me put here square bracket. And plus, so from this piece, we are going to have x times, right, 8 over x, where this x and x is gone. So we have only left 8. So let's simplify. Second derivative of x is equal x to power 6. And we have 56 natural log x plus 7 and plus 8, right? In equal x to power 6, 56 natural log x plus 15. Okay, so once we have it, now we can explore second derivative. We have product. So to get f the second derivative of x to check on concavity up, which means get to positive, so we have to get either both these terms positive, right? X to power 6 greater than 0 and 56 natural log x plus 15 greater than 0, or it has to be negative, right? Less than 0. 56 natural log x plus 15 less than 0. 15 less than 0. Now this one cannot happen because x to power 6 we have even degree. It can never be 0. Right? Only just because of that, I don't even have to look into second inequality. The first one doesn't satisfy, so I drop it. Right? Actually, I can drop this way. All right? So, we have only one case to look into. So, we know that x to power 6 is greater than 0. Which means I can say that x cannot be equal, hence x cannot be equal 0, right? And because if x is 0, I'm getting the x is equal 0, which is going to be just about inflection point. So I'm for positive 1, my x cannot be equal 0. And for 56, logarithm x plus 15 greater than 0, I can say that natural log x, it's going to be greater than negative 15 over 56, right? And from here, I can say that x is greater than, so here we have base e. So remember, definition of a logarithm, base to raised to power, we are getting result, which in this case, it's going to be e to power negative 15 over 56, right? Okay, so just to remind you that domain has to be all positive real numbers because we have logarithm, correct? Therefore, so this result we are going to break down into 3 cases. First case, so when if x is greater than negative 15 over 56, then we get our second derivative greater than 0, right? Which means what? Absolutely correct. Concavity up. So concave up. Function f is concave up. And if we have x is less than, let me write down, x is less than the e to power negative 15 over 56 and greater than 0, right? So between 0, since we have restriction, cannot be negative. Therefore, from 0 to e to negative 15 over 56. And plus, I don't put equal sign where it comes to 0. Otherwise, I can't have the concavity. So it's going to be f second derivative. It's going to be, in this case, less than 0. You can try and you will see. And we will get concave down. And now let's explore when x is equal. If x is equal negative to power negative 15 over 56. And so if it's equal, then f second derivative of x is equal 0, right? And therefore, what do we get? So if it's, we have, this is our point at x, or e to power negative 15 over 56, right? So less than the e to power negative 15 over 56. Let me rewrite it. E to power negative 15 over 56. Which is going to be less than. So when we have less than, it's going to be concave down. It's right here, right? Concave down. And if it's on the right side, in nearest surroundings, so we are getting concave up. So here we get down, here we get up, which means if from down is switching to up, that means that we are facing inflection point plus this inflection point is failing because it's gonna look like this. Why is not looking like this? Because on the left side we have second derivative down, right, less than 0. And on the right side, we have second derivative up. Let me write down here. That's why. Okay, And that's it. We already know the intervals. On interval where x point is greater than e to power negative 15 over 56, the function is concave up. When x is between 0 and e to power negative 15 over 16, the function is concave down, down. And when x is equal e to power negative 15 over 56, we figured out that we have inflection point. Okie dokie.